Okay, the first concept here is something called work. Okay, work. There's three things in chapter 9 in this unit: work, energy, and simple machines. Yes? Now, you know what forces are. We've done forces. Yes? If I lift something up, if I take this, which is actually very heavy, and I lift this, I'm doing work by lifting this. Understood? Now, I don't mean going to work, being a teacher, or going to work, being a student. That's not what I'm talking about. I'm talking about the physics definition of work. And the physics definition of work is actually very simple. It simply goes work, small w, equals force times distance. Understood? Force times distance. So that would be newtons, right? Newtons times meters would be the unit labels, or let's look at the unit labels a little bit more carefully. So newtons, we know, is kilogram meters per second squared. Correct? Yes? Is that true? If we multiply that times meters, we get kilogram meters squared per second squared. Correct? Yes? So, the unit labels for work are actually this: kilogram meters squared over second squared. Clear? Make sense? Yes? Please don't say yes if you don't understand. You get that? Okay. Now, let's talk about this work. Definition. Work is force times distance. Unit labels are Newton meters or kilogram meters squared per second squared. Let me show you something. Let me show you something. You've heard of, in middle school and chemistry and possibly biology, something called kinetic energy. Correct? Have you? You know what that is, right? Yes? Okay. Temperature is the average kinetic energy of a substance, for instance. Definition of temperature. In AP chemistry, we've gone over that, right? Yes? We know that this is 1/2 mv squared. Correct? We know that that's 1/2 mv squared. Yes? Okay. So this is going to be kilograms, meters over second squared, would be meters squared over second squared. Correct? Yes, Mary.
You said force is...
What is it?
You said work is force times distance.
Correct. Now we're looking at kinetic energy for a moment. So the unit labels for kinetic energy are 1/2 m kilogram. Velocity squared is m over s squared, would be m squared over s squared. So that is the unit labels for kinetic energy. Look at the unit labels for work. Same. It's the same. Correct? One more thing. Let's look at potential energy. Let's look at potential energy. Correct? Potential energy equation is m. What is it? What's the unit label for potential energy? mgh. potential energy, correct? Yes? So this is going to be kilograms. G is meters per second squared, and height is in meters. So we'll put on another meters. Clear? Yes? You get that? So that is potential energy. Yes? This is potential energy. This is kinetic energy. And this is work. What do you notice about work? It's a form of energy. And this is potential energy. This is kinetic energy. And this is actually, we call it mechanical energy. Okay? Mechanical energy. Yes? And we have a very special unit label for that. There's no problem with calling work Newton meter. How many Newton meters is it? That's okay. It's okay. Okay, I'm not going to go crazy with that. If you want to say Newton meter, can I erase this? Can I erase it? If you want me to say, if you want to say Newton meter for work, you can do that. Okay, this marker is just absolutely awful. Okay, so if you want to say force equals, work equals force times distance. If you want to say Newton meter, you can do that. But we have a very special unit label for work. If you want to say, I apologize, let me back up for a second. Kilogram, meter squared, second squared. You want to say that too, that's fine. It's not a problem. But the unit label we use for work, accepted unit label we use, is called the joule. After scientist, Professor Joule, Dr. Joule, whatever. He was a scientist. That was his name. Family name, Joule. Okay? And we just simply use the J. You have Newton after Isaac Newton. You have Joule. Look up Joule, the Professor Joule. Four of them. Misa, do that for me, please. Joule. Understood? You get it? Easy? Yes? Let's do a problem with this in mind. I got to erase the board soon, so I can't really do a lot with this. Okay? All right? Can I erase some of this? As terrible as that may be, we just work here. Okay, so let me do exercise 1. It says, on his way off to college, Russell drags his suitcase 15 meters from the door of his house to the car at a constant speed with a horizontal force of 95 newtons. Okay, so on his way off to college, Russell drags his suitcase 15 meters. Right? That's the distance. Right? And with a horizontal force of 95 newtons. Right? How much work does Russell do to overcome the force of friction? So he's dragging it at a constant speed. They don't tell you what that speed is. They're just telling you that it's constant. What are they telling you when they say that it's at a constant speed? What are they telling you? They're telling you that the force that you're applying is the force that's overcoming friction. If I take this chair and I go to constant speed to keep it going, this is on wheels, the only force that I'm applying to keep it at constant speed is the force that overcomes the friction. So if I can determine the work done to overcome the friction, that's the answer. So it says, how much work does Russell do to overcome the friction? So it would be work equals force times distance. Work equals 95 times 15. So the work is what? What's 95 times 15? All right, we have 1425. 1425 joules. Okay? 1425 joules, yes. You don't write newtons. Yeah, because this is at, let me do this a little bit more clearly. This is work equals 95 newtons times 15 meters. Right? And we know that Newton meters is joules. Okay? I'm trying to make it easy by saying just call it joules, not harder. And then it says, if the floor has been waxed, does he have to do more work or less work to move the suitcase? Why would it be less work? The distance is the same. 15 meters is 15 meters. This is important later on. But why is it less work? There's less friction because the floor's wet. So that value would be less. The force would be less because the friction is less. The friction is less, the amount of work that you're doing is less because it's just sliding. If I took this chair and took the wheels off it, it would be harder to move it, right? Of course, makes sense. So the work would be greater if I took the wheels off it. So, but what's constant? The thing that's constant is the 15 meters. That's going to play an important role later on in this. Okay, are we finished? Number one, yes? Yes, let me stop it then.